turn these suckers off, if you don't mind. Welcome, everybody. John Jr., Vice President of Geology, Jack Cole, and also the Vice President here this evening. It's my pleasure to introduce our speaker tonight, Bob Biek. He is a senior scientist with the Utah Geological Survey with their geologic mapping program. He joined the group in 1996. As he notes here, after 4 years and exclamation point 5 winters as a mapping geologist with the North Dakota Geological Survey. And most of his mapping is in southwestern Utah and then also along the Wasatch Front. He's the lead author of 36 7.5-minute geologic maps and of the St. George, Anguich, and Loa 30 by 60 quad maps, that represents a lot of work. So geologic mapping, as he said, is in his blood. He's continually amazed at what one can learn simply by going outdoors and making a geologic map, even of areas that have been previously mapped. And he's also been instrumental in the discovery of Utah's gigantic gravity slides. And these are, it's a good example of what you can find, what you can see if you go out and look around. And that's, of course, what Bob's going to talk with us about tonight. He received a degree in geology from the University of California, Berkeley, and a master's in geology from Northern Illinois University in 1987. So without further ado, I'd ask you to join me in welcoming Bob Biek.
Great. And is that turned on?
Yes, it's on.
Okay.
So, and you're on.
And I'm on. Great. Thank you, John. It's good to be here. There's actually not many people that get to do the work that I do. Nationwide, there's probably fewer than 100 of us. I work for the Utah Geological Survey. I'm a geologic mapper. So I spend a lot of time out just hiking around, looking at rocks, and it's a really sweet gig. But nationwide, not many people get to do that. And by and large, we don't really go out looking for things. We're quadrangle mappers. And so we go out there and we observe and we make our maps. We make these multi-purpose geologic maps that are used for a variety of, planning and research and educational uses. But once in a while, we actually do make big discoveries just through our mapping. And with regards to these really gigantic landslides that I'm going to show you, I can't say that there's really one eureka moment where I've been, working for years and years and everything finally kind of became clear. But I had a lot of what I like to call that's weird moments, where I'm out there, I'm all alone, I come across an outcrop that is just so weird and so confusing and just so unexpected that I have to abandon one hypothesis and work to kind of craft another. So it was through a series of events like this that we kind of stumbled upon, working with my colleagues David Hacker and Pete Rowley, actually not just 2, but 3 of the largest landslides on land known in the world. So some pretty neat stuff we're going to see. Kind of the goals for tonight, I want to show you, introduce these 3 slides and show you some examples of the types of really amazing deformation we see in these rocks. Talk a bit about the extent of these slides and when they formed, and talk about what we think actually happened to create these gigantic slides. And then, if the past is any key to the present, I'm going to look out here and I'm going to see a lot of kind of stunned faces, honestly. Maybe some shaking heads, I don't know. But what I'm going to show you is really, I think, really amazing. And then just very briefly at the end, I want to just run through some of the new research that is being done with these slides. Yes?
Go back and tell us what the background was there.
The background, we will learn about this. It's something pretty amazing. But I want to start out with, and actually, if there's something I'm talking about that you don't understand, go ahead and ask. I'll try to clarify that. But I want to save time, too, for questions at the end. I know you're going to have questions after seeing this. I actually have some rock samples over here of the kinds of deformation that we're seeing, so we can look at those. And tomorrow, lunchtime, I'm going to get into more of the history of the discovery of these slides, which in itself I think is a really fascinating story, but won't really get into that here.
At the Senior Center,
Yeah, tomorrow at the Senior Center at noon.
open to the public.
Yep. So here, simple XY plot showing the worldwide distribution of landslides, okay? Numbers getting bigger away from the origin, the number versus size. And what this shows is that most landslides are kind of small, smallish. But look at this, see if I can get this to work, cool. That little peak, it shows that there are actually some truly gigantic landslides out there that we know of. Now we could talk about some higher math here. We could talk about probability, for example, and that's really easy to do. Just write the word probability on this chart. And what it shows, of course, are landslides. Small slides are really common. Gigantic landslides are really rare. So, you know, who cares? It turns out there's a group of researchers that are really intrigued with these things from kind of a mobility point of view, trying to understand how truly gigantic landslides can travel across the surface of the Earth, the former land surface, tens of kilometers, when classical physics tells us they should not be moving at all. And that's not really my interest, mostly actually because it does involve a lot of math. My interest is in trying to understand the extent and the characteristics of these big Utah slides. And then in the back of my mind, I keep thinking about, we know of 4 truly gigantic landslides in the world, right? 3 I'm going to show you tonight, and 1 other that you've probably heard about, Heart Mountain, here in northwestern Wyoming. Those are the 4. Okay, they're all in the western US. I don't believe for a minute that that's all that's out there in the world. I think that once geologists start to realize that these superficial processes of landsliding can produce structures so large that they're actually mistaken for tectonic features. You know, once we realize that, we're going to start seeing these, I think, elsewhere in the world. So I think that's really actually pretty exciting. So that's kind of my take-home maybe message for tonight. Ask yourself that question. Okay, there are 4, all in the western US. I don't believe that. They're out there. We haven't found them yet, but I think people will start recognizing them. So just to introduce where we're talking about, basic geologic map of Utah, we're talking about, this is really cool. I like this. This area in pink, this is what we call the Marysville volcanic field. And it's maybe 120 kilometers in diameter. It was active from about 30 to 15 million years ago. And today, it consists of the very deeply eroded remains of cascade-like stratovolcanoes and other volcanic vents, and 3 large Yellowstone-like calderas. And it is built on a very weak substrate of clay-rich volcaniclastic rocks. And that's going to kind of be, you can guess, important to our story here. But the other interesting thing, about this field is that there are interbedded ash flow tuffs erupted from calderas that are on the present-day Utah-Nevada border here, you know, some 80 miles to the west. And those are really interesting and important units in this story in that they're easily recognizable, they're very distinctive, and they erupted and were deposited basically in a geological instant. And so they preserve a record of the landscape and the structures that existed at the time those erupted. And so they allow us not only to kind of understand this period of basin range extension all across Nevada and western Utah, to kind of piece that story back together, but also this earlier story of the gravitational collapse of this volcanic field.
Bob, on that map,
Yes.
About where would I-15 be? And maybe
Yeah, good,
Cedar
good.
City?
Yeah, thank you. This is I-15 coming right down through here. Cedar City is, whoops, it's actually a little hard to use. Cedar City is right down in here. Zion National Park, of course, is down in the corner of the state here. We've discovered, like I say, 3 gigantic gravity slides. And the first that we discovered is what we call this Markagunt gravity slide, discovered in 2013. In 2016, we discovered the severe gravity slide. And these are named after the plateaus where their remains were kind of first discovered. And since I was talking to John about giving this presentation, we discovered a third one just this past summer. We call the Black Mountains gravity slide. So I want you to think of each of these as, like a 1 mile or 2 mile thick southward tapering wedge of volcanic rocks, these andesitic lava flows and lahars and these interbedded ignimbrites that failed catastrophically from the north to the south. Let's see. Oh, and it was importantly, this was preceded by slow kind of gravitational spreading of this volcanic field, and that's a common, it happens at volcanoes worldwide. The Earth's crust does a really poor job of supporting these massive volcanoes, and so the Earth's crust just kind of spreads out, oozes out. This happens in Hawaii and Mount Etna, and any big volcano is doing this. And so here, it spread, it's kind of funny, this kind of thing goes backwards, but spread southward under its own mass before each of these slides happened. Now I'm not going to kind of harp on the size of these, but I want to give you a feel for really how big they are. If we were to superimpose the outline of these slides to scale on a Google Earth image of northwestern Wyoming, here we are in Jackson, Yellowstone Lake up here. These things are 60 miles long. They would stretch from the west side of the Tetons over into the Absarokas. They're insanely big. Collectively, they cover an area the size of Yellowstone National Park. And the volume of these things is enough to fill the Grand Canyon to the rim and then some. So they're really, really insanely massive things. And this is kind of, again, I'll tell you more about it. Hopefully some of you can come tomorrow and learn more about the history of the discovery. But for me, this is where it all started. This is a place called Haycock Mountain. And it's near Panguitch Lake on the plateau up above Cedar City in southwestern Utah. And it doesn't look like much, right? It doesn't look like the Tetons. It's not spectacular. But in my 30 years of mapping, this is probably my favorite place in all of Utah. And so what we're looking at here are 2 different rock types. This TBH stands for the Tertiary Brine Head Formation. And it is this clay-rich lake and floodplain deposits that form the base of the volcanic section. And then on top of it, that brown layer is what we call the Isom Formation. And it's an ash flow tuff erupted from a caldera on the Utah-Nevada border 27 million years ago. And so that, in this area, this is a normal section. Nothing here looks unusual. And that's what people had thought in the past. And that's actually why I went here, to scramble up these cliffs, look at those rocks, and get to know them so I could map them. But when I got up to the base of the Isom, I didn't see what I was expecting to see. This is one of these that's weird sort of moments. This is what I saw. And 2 important points here. One is that this Isom is utterly fractured and broken. And then secondly, it's underlain by this very sharp, I can't quite get this to work. It won't, there it goes. Well, that sharp planar surface. And below that is about a 3-foot thick layer that we call a basal layer. So let's talk about each of those things. That the isome, this is a really densely welded asphalt tuff. It's a really hard rock, but here it's been crushed into sand and gravel-sized pieces and then relithified. It's what we call a cataclysite. And if you looked at that in thin section, and this kind of larger fragment here is about 0.5 millimeter in diameter, so a thin slice of rock that you look at under the microscope, you can see fragments of this very densely welded ash flow tuff here, just encased in this matrix of ground up isome formation. So it's a rock that has been just severely deformed by brittle fracturing. And even kind of more interesting than that to me is it is underlain by this unit that we call this basal layer. And that basal layer consists of ground up upper plate and lower plate rocks that behaved as an overpressured fluid. And that's served to reduce friction at the base of this slide. And it was actually injected into fractures, these kind of reddish brown stained fractures into the broken upper plate as this slide came to a rest. And furthermore, the base of that slide, it's a fault, okay? Here it's just kind of horizontal. Often we think of faults as more or less vertical, but this is horizontal. And it is grooved and striated. It's like it's got skid marks on the base of it. And those skid marks tell us that the upper plate came from the north to the south. And that's, I think, pretty cool. See, where am I going here? Yeah, let me back up one more. So this basal layer in these, what we call these injectites or these clastic dikes, we find them at the base of these slides, wherever we see the base well exposed. And they're diagnostic evidence of emplacement by landsliding versus by some other faulting tectonic process. So the really important things that we're looking at here. But the discovery that kind of really took our breath away came, and I should say that was back in 2008 when I discovered this outcrop. Shortly after I started working in this area, and that was actually it was actually 11 years ago to today that I was here, and that you might remember was just a couple weeks after this really bad day in September 29th, 2008, the market crash. So it was a really nice day to be out into the field, away from the TV, you know, away from internet access. And this is what I stumbled across, so it was pretty cool. But again, this discovery is what kind of blew this whole thing wide open. In this, we're looking at two different rock layers here. Again, a normal stratigraphic section. From a distance, you'd say, okay, as a mapper, you'd put your line on the map and move on. And that's exactly, unfortunately, what I did. But when I told David Hacker, he's an expert in these shallow igneous intrusions called Laccoliths that come up into the shallow crust and inflate the crust and shed big landslides off them. So he was working on smaller slides nearby, and I said, David, you got to come over and look at this. And he did. He hasn't been back to his old field area for 10 years now, but in the interim, in 2013, he discovered this site. And what is interesting here is that we've got a sandstone below and these volcanic mud flow deposits above, so maybe not too exciting, but that contact, it's not a normal depositional contact, it's a fault. And it's a fault that is lined with obsidian-like glass. And that glass is injected as dikes into both lower plate and upper plate rocks. So it's just, I mean, it's really neat stuff. If you look down on that fault surface, you see it's vesicular, it's kind of got flow features in it. Most of it looks like just beautiful black obsidian. It's not obsidian though, it's actually a mafic glass. It's very low in silica. It is of basaltic composition, and it was derived from the melt from friction on this sliding surface. If you look at this in thin section, this is what you see, not a lot. In glass under cross nickels, it's isotropic. So you see a few partly melted mineral grains, and if you uncross the nickels, this is what you see. It's just a really beautiful glass. There's some flow features around these relict grains. But what is really important about this, and what I love to say, is that it's a pseudotachelite, okay? And that's kind of a weird word, but it's a really rare type of rock that is produced on the deeply buried portions of fault zones, deep in the Earth's crust, down at a depth of 5 miles or 10 miles deep in the Earth's crust. And it's also known from big impact events. But this is the first reported occurrence of this glass, this pseudotachelite, on fault surfaces on landslide-generated pseudotachelite. So it's the first example known in North America. And it's one of the few examples actually known in the world. There's only half a dozen or so places in the world where people have seen this. And so it's really amazing stuff. And it's important not just for that reason, but because it implies, it tells us that this emplacement event had to be fast, right? You've got to, you couldn't just creep along and generate the heat that you need to melt that glass. It had to be fast. And that's a question we often get is, well, okay, so how fast did these slides go? And we've got people working on that right now. And so I don't have a number for you, but eventually we will. But from what I understand so far is that if we were to time travel back in time to when this event happened 23 million years ago, and we were traveling on Interstate 15 from this small town of Beaver to Cedar City, and we were going 80 miles an hour, which is the speed limit, this would have gone right over us. We think it was probably going 50 to 100 meters per second. Over 100 to 200 miles an hour. So just a huge catastrophic emplacement event. And this is we think, some pretty good evidence for that.
What kind of temperature?
The temperature, yeah, what's the temperature of this? We know to melt this rock, it's got to be at least 1,500 degrees Fahrenheit, 800 degrees Celsius, but probably a fair bit more than that. And we found this pseudotachelite now on probably a dozen different localities on these slides. No one had ever seen this before.
Are you going to talk about how it achieves that velocity? How does it get going?
Yeah, good question. We'll get to that. We'll get to that, about how do you get that speed in the first place. This is just a cartoon showing these 3 slides. I've been showing some of the rocks from this green slide. That's our Markagunt gravity slide. In yellow is the Severe gravity slide named after the Severe Plateau. And in blue is this Black Mountains gravity slide. What I want to do now is jump over to this area on the Severe gravity slide. A few years ago, I'd wrapped up mapping around this area, and so I'm moving kitty corner into a new project. I'm off this mega slide business, which I thought was kind of great because it's really complicated. I could finally go into some normal volcanic rocks and start mapping and start to cover some ground. Well, one of the first places I went to, right here, this is what I found. And here we're looking north along a fault zone here that drops these kind of gray volcanic rocks down against the yellow tan pre-volcanic rocks. So it's splay on one of these big normal faults that's breaking up the western part of the Colorado Plateau. So not real exciting, but notice this at the top of the arrows. This, can't keep this thing down. Very sharp planar surface. If you look at that up close, what you see, this sharp surface, these rocks above are just utterly destroyed volcanic rocks. Rocks below, you can see they're still well bedded and undeformed. You walk over there and you look at that surface, You see it is grooved and striated and fractured. Those are skid marks again. And we can say that that damaged upper plate moved from the north to the south. And there's a basal layer here again. There's these clastic dikes, or injectites as we call them. Here's a hammer for scale. This resistant fin is one of those. And these things extend for 30, 40, 50 feet above that basal slip surface up into the fractured upper plate. And so, again, that is diagnostic evidence of overpressured fluids at the base of these slides that help to reduce the friction on that surface. This is one of those days that I'm working out in the field. I'm all alone. It's a beautiful day. And a big old smile comes across my face, because I recognize this guy. This is like recognizing an old friend, but I admit I didn't really want to see this here, but we found it. And so I got back to the motel that night, and I called Pete Rowley. And Pete worked with the USGS his whole career, worked in these volcanic rocks. And I told him about this, and he said, Bob, I saw something like that in the mid-1960s on the heart of the Severe Plateau where he did his dissertation. So we were talking, and I said, okay, we really have to look at this whole plateau and see what's going on. And we did. We went to the very south end of the plateau, and this is not far north of Bryce Canyon National Park. There's millions of people that go to Bryce every year. My brother Don was just there actually going hiking. They go for the red rocks, for the hoodoos, for this incredible scenery. And you can see this from the overlooks. If you look north, you see this kind of gray and brown cliffs in the distance. That's this. What a snoozer, volcanic rocks. But this is anything but boring. This is our Bryan Head Formation again, a greasy substrate. And it's overlain here not by the Mount Dutton Formation, but by a different rock formation we call the Mount Dutton Formation, volcanic mud flow deposits. Except the contact between them isn't anything but normal. That big cliff is one of these basal layers. And it's not just, the basal layers can be a millimeter thick, they can be a meter thick. Here, it's nearly 100 feet thick. Big chunks of that have rolled down. You can go look at them, like walk up to that block. And what is cool about them, the basal layers kind of look like concrete or glacial till. It's very poorly sorted debris. And this is what is cool. It contains these elongated, stretched out, not just cataclastically deformed rock, not just crushed, but just what we call ultra-cataclastic, crushed almost beyond recognition. But these are fragments of those distinctive ash flow tuffs. And if you look close at those, I called them Taffy Rocks, because to me it kind of looks like taffy. They've been kind of stretched like that. And on a field trip that I'll tell you about in a minute, people really took exception to that because they're not plastically deformed, they're brittly deformed. And some of them have really delicate structures, tails on them that are just incredibly delicate looking things that somehow form during this chaotic flow. If you walk up to the cliff itself, here we're looking kind of straight up, and these things are shiny, they're silicified in this view. But the length to width ratios on these are just huge. They've been stretched out just for, by incredible amounts. Here's another view of nearby at the south end of the Severe Plateau. And again, our friend, the Bryan Head Formation. And at the top of the arrows, a thin basal layer. But look at that cliff above. All looks kind of weird. If you look closely at that, you see each resistant ledge is one of these lava flows or a flow fragment that has just been crushed and then kind of rehealed. And it's encased in this structureless brown sand that's recycled Bryan Head debris. So it could be that whole cliff actually is some sort of weird basal layer that we don't fully understand. In places, again on the severe plateau, the base of this slide contains just really astounding deformation. You get chunks of brine head formation that are thrust up into the base of the slide, and this is, you know, that big piece right here. So pretty astounding types of deformation.
Was that piece rooted?
I'm sorry?
Was that piece rooted?
Is this piece rooted? You know, I've actually not been up here. I don't know if it's rooted or if it's just floating up in the base of the slide. In places, the brine head formation, you can kind of see the contact between the mud flows here and the brine head, this stuff. But the upper part of the brine head is full of these south-directed small folds and thrust faults, kind of a distributed zone of deformation through there. And in places way high up in the slide, we're hundreds of feet above the base now, you get subsidiary small shear zones. And this is one, that real sharp, this real sharp surface there that I'm kind of standing on, you can see projects up to the upper right, is actually a shear that, guess what, is lined again with this friction-generated melt, this pseudotachelite. And there's just beautiful injection features in this area, again, way up high above the base. So evidence of overpressured fluids that are helping to move these things along. Now,
Tan rock that was injected there?
I'm sorry?
What is the tan rock that's injected there?
This is basal layer debris that's been fluidized and is injected into fractures in the upper plate. So it's just ground up host rock. But you've got to ask yourself now, we see this kind of deformation all over these slides, especially when you get down near the base where all the action is going on. But you've got to ask yourself, how do we know that this is truly from landsliding versus from some other process? How do we know it's not primary volcanic debris avalanche deposits, for example? Or how do we know it's not a low-angle detachment fault, a fault that is rooted deep into the Earth's crust? And we argue that it's really at the bottom of the slide where we find what we consider diagnostic evidence of that. And it's these basal layers and injectites that are evidence of that overpressured fluid at the base of the slides. The pseudotachelite tells us it had to be fast, it couldn't just creep along. But it's the basal slip surface itself that's really important too, because if you think about Utah geology, I guess I didn't explain this, but the volcanic field is built over the leading edge of the severe fold and thrust belt. So this late Cretaceous, early Tertiary orogenic belt. And all that deformation is oriented from west to east. All of this deformation is oriented from north to south at right angles to that. And it involves rocks younger than that earlier orogeny. And it's also cut by high-angle basin range normal faults. And so we get longitudinal cross-sections through these slides where we can see these basal slip surfaces. And we can see that the faults are not rooted, but they daylight. And they daylight at a structure we call the ramp fault. And so here we're looking east on the Markagunt Plateau. In this cliff is our Isom ledge. And everything to the north of that, to the left, is our upper plate rocks that are being thrust up onto the former land surface. And these little knobs on top of the Isom are older volcanic rocks then thrust up on top of younger volcanic rocks. And so we can show that this basal fault, it's not a detachment fault, it's not a tectonically rooted fault, but it daylights like a landslide fault does. let's see, timing. We've actually got pretty good constraints on when all this happened. For the severe gravity slide from, you can see, 25 to 25.4, and these are based on cross-cutting relationships of deformed and undeformed rocks. The Markagunt slide is 22.8 to 23, and the Black Mountain slide we don't have tightly constrained yet. We're still trying to understand that thing. So these are latest Oligocene to early Miocene events, kind of at the height of this Marysville volcanism. And here's what then, excuse me, what we think is going. These are a before and after kind of cartoon to explain what we think is happening. And again, the Marysville volcanic field here is built on this really weak substrate, this red layer of the Bryan Head Formation, these clay-rich altered volcanic ashes. And so you get that volcanic field growing on this weak foundation. During the later stages of the evolution of that field, as it's inflating, something happened. We don't really know what happened, an earthquake, a volcanic eruption or something, but something happened to trigger these slides. And this is just another cartoon of what we think maybe the Markagunt slide looked like. And like a modern landslide, it consists of you know, several different parts, all right? It's got a breakaway zone where you see extensional deformation. It's got this bedding plane slip surface where we see simple translation, where we get blocks that are you know, 10 square miles or more in extent that have just undergone simple translation, maybe a little rotation, but are otherwise not that badly deformed until you get down to the base of it and you start to see all this tremendous deformation. We find, of course, the ramp fault where it ramped up onto the former land surface. And there you can imagine you get extreme compressional deformation. You get thrusting and folding. You get older rocks shoved on top of younger rocks, like you do out here on the former land surface. And then finally, at the leading edge, we see what we call debris avalanche deposits, where this slide mass is just, you know, disaggregated into a chaos of debris. So we've got the severe gravity slide here. Again, this is just the Marysville volcanic field in pink. The severe slide, the Markagunt gravity slide, the Black Mountains gravity slide, and our ages. And notice that it forms kind of a westward progression from 25 to 23 to less than 22. And that mimics the height of volcanism as it progressed westward across the field. So kind of interesting. We know it was preceded by, by slow spreading along this, what we call the Markagunt thrust fault system. Just like modern volcanoes, that the Earth's crust is just failing out in front of them. What I find intriguing, and maybe to get to your question about speed and why these things happened, the short answer is we don't know yet. But what I find intriguing is that the head of each one is a major volcanic feature. Here we've got the Monroe Peak caldera at the head of the severe gravity slide. Here we've got the Mount Belknap caldera at the head of the Markagunt slide. At the head of the Black Mountains, we don't have a caldera, but we have Utah's largest exposed granite batholith. People have interpreted that as a core complex. And I think it has pretty strong implications actually for what the mineral mountains actually are. They seem to be related, you know, to this big slide mass to the south, but we have yet to work that out. Let me think. Yeah. So let me shift gears here. And in 2017, David, Pete, and I convened a week-long GSA-sponsored what they call Thompson Field Forum. We brought together 30 people from around the world, experts in rock mechanics and volcanology and structure and tectonics and all of this. And we spent 6 days on the outcrop, which was one of the most amazing experiences in my life, actually, to get some really intelligent people out there to look at what we're finding and say, what up with this? It was really amazing. As a result of this, we've got a field guide in press that should be out later this year. We list 70-some different sites that you can go to see this sort of deformation. So that is, I'm really looking forward to seeing this come out. And then I just want to real briefly run through some of the research that people are doing now. We have over half a dozen students that are doing research on these slides or have completed research already. And this is the first student, and I'm going to space on the name, but David Hacker, his first student that did some really good mapping of a really difficult part of the ramp fault, where you get just amazing compressional deformation in older on younger structures. David's next student, Shannon Hunter here, looked at the Haycock Mountain tuff, which constrains the upper age limit of one of these gravity slides, showing where that tuff came from. And then his latest student, Zach Loffer, was just out this past summer, spent 3 months mapping and camping on this severe gravity slide and finding all sorts of amazing things. Pseudotacholite in multiple places and these injectite features, and he's having a ball. Ashley Griffith here and his PhD student Mike Bronigal are really, they're the people interested in the mechanics of this, trying to understand how it can move 35 kilometers over the former land surface and at what rates of speed. He actually is leading a joint NSF proposal. He's at Ohio State that they're going to submit to the Tectonics Division of GSA in the next month or two. And let's see who we got. Tiffany Rivera and her student McKenna Holiday have done a lot of dating for us. And Barb Nash, who's not shown here, but works with Pete Lippert at the University of Utah, has done some work on these pseudotacholites to tell us the chemistry of those and maybe what they're derived from. Eric Farah here, he's a paleomagician out of Louisiana State University, and we took him on this field forum to this pseudotacholite outcrop and almost couldn't get him to leave. He just said, pick me up in the morning, I'll be fine. He was so enthralled with this. And he's got his own separate NSF proposal to look at this glass and compare it to glass in Austria and in the Himalayas. Zach Smith, he was an undergrad at SUU in Cedar City, taught himself structures, taught himself geologic mapping, did a phenomenal map of part of the ramp fault. And also as an undergrad now at UNLV, Kevin Rafferty did a lot of work on a rock unit that looks a lot like the Brine Head, but is not the Brine Head, is actually, turns out, is debris that's eroded off these gravity slides into a little basin out in front. So he's kind of worked out that story. And finally, Dave Malone here of Heart Mountain fame. He and his students have been using detrital zircon geochronology to date basal layers to give us another independent way to date these slides. So a lot of research actually is going on in just a few short years since these things have been discovered. And that, just wrap up. These slides are nothing we went looking for, but we were out mapping, and they're really amazing things. Tomorrow at lunchtime, I'm going to tell you more about kind of the history of discovery of these, because there's I think some really interesting stories on how this all came to be. It's not all my work, it's not all David and Pete's. It has an early history of people seeing parts of this big, vast elephant, but not being able to put it together. So happy to answer any questions. And again, we've got some samples of the glass and things over there for you to look at. And yeah, thank you. So. Yeah, yeah.
I'm intrigued by the pseudo-tachylites. It looks like the rock above and below the slide plane are not mafic.
Right.
And so to come up with a mafic tachylites,
Yeah.
there must have been some kind of fractionation
Okay.
of the material.
Good question. The question is, why is the glass of basaltic composition? Why is it mafic? You know, an obsidian is rhyolitic. You know, it's very silicious. It's kind of the end member of this whole system. But this is truly basaltic in composition. And we think what's happening is that sandstone underneath is biotite rich. So maybe the biotite is preferentially melting to contribute to that glass. We don't know for sure, but that's, again, something that people are eventually going to figure out. I'm just a mapper. I see this stuff, and I was really fortunate to bring in a lot of really sharp people that are now going to start to do research on characterizing that glass and telling us what sort of pressure, temperatures, conditions it formed under, and what that means for speeds of emplacement and all that stuff. But I think why it's mafic is, you're right, the rocks are not mafic, they're andesitic, so something is preferentially melting to make it that way. Yeah. Yeah.
What happened, so there's a slide in rock debris,
Mhm.
then what happened after? Did it get reburied again, or did it just stay kind of where it slid?
Right. So these slides happened, and I think I forgot to say that. This is all pre-basin range deformation. So this was a high elevation plateau, pretty featureless, a lot of volcanic mountains. And so these slides happened, boom, they come out, and they sat there for millions of years. And they actually influenced the distribution of these regional ash flow tuffs that erupted, you know, from way far to the west, and are being entrained in paleo valleys, and they hit these slides and stop. They don't go beyond them. So there's kind of a neat story there. But they happen, they sit there, they happen, they sit there, happened again. And then, you know, some maybe 5 million years later, basin range extension happens, starts to break things apart, and things get buried and eroded. So today, when you're driving down I-15, you look out there and you see beautiful mountains. You have no reason to think that those are landslides. They don't look like landslides, but they have all the components of a landslide. They have the extension, the translation, the compression. So we think it's a really sweet model to tie everything together. Yeah. Yeah.
How much of a gradient is required?
Yeah, always get this question. I love it. I have no idea. The question is, you know, what kind of slope do you need to create runouts of 20 miles or more? And right now, the slope is opposite because of basin range deformation. The toe is higher than a lot of the slide mass. So there's that deformation we have to kind of undo to try to get at paleo slopes. And we've got people on this NSF proposal that are going to look at paleo elevations using isotope geochemistry of the glasses and of carbonates. So hopefully we'll get some constraint on that, but my guess is you don't need much of a slope at all. I would guess less than a degree to flat. So, and think about it, you know, if we're talking about runouts of 20 miles, if you put on a big slope, you know, pretty soon you're going to be up at 100,000 feet. I just don't think you need a big slope. I think you need to have this huge mass fail and somehow give some, you know, oomph to push that out. But the short answer is we don't know for sure.
Somewhat dependent on the clay types and the...
It's dependent, I think, right. You know, how do you reduce friction on the base of the slide? And people have come up with all sorts of ideas on acoustical fluidization or fragmentation and spreading, or hydroplaning, or on Heart Mountain they talk about thermal decomposition of carbonates and CO2 generation. Something has to happen on the base to enable it to slide. And here, what we see are these basal layers. So that it's an overpressured fluid that this thing is riding on. And that implies, you know, there was a certain amount of water there to make that. But basically I think the basal layers are an integral part of it. And the basal layers can be, like I said, super, super thin, rock on rock, or they can be 100 feet thick. So, yeah.
Now, on your basal layers, you're saying they're fluid. Are they hot fluid?
Good question. We think it is, actually. And at least on a severe slide, there's evidence of some low temperature hydrothermal minerals. And I don't know much about that, but those fluids probably were hot. At the base, we see the basal layers. We don't always see pseudotacholite there. And so, you know, maybe if the rocks are dry, you get pseudotacholite, and if they're wet, you get the basal layer. I don't know.
But look on the severe and on your middle one.
Yeah.
Up where things seem to start as far as the slide were calderas, you said.
Mm-hmm.
So
That's a good point. Yeah.
I'm trying to think, is there some motion that got this all started? Or
Yeah, I think I failed to make that point. The slides happened, you remember, 25, 23, post 22. The caldera at the head of the 25 MA slide is actually 23 MA. Oh, okay, I don't like that. On the Markagunt slide, it's 23 MA. When that event happened, the caldera is like 19. And so they're younger, so they're not directly related. But the fact that they're at the head of the slide still makes me wonder about some sort of causal connection. Inflation. And what seems to have happened is that when these slides happen, we didn't get a huge volcanic eruption. You think you would. You know, if you release that sort of pressure on a volcanic field, you know, boom. That's what these shallow laccoliths do that David Hackers works on. So I can't say we really understand what's going on there, but to me it's a weird coincidence to see a big structure at the head of this thing, even if the ages right now, as we understand them, don't quite work. Yeah. Yeah, in the back.
Do you think one of those slides could happen underwater?
Thank you. Good question. Yeah. In fact, the ocean basins are full of gigantic landslides, far bigger than Heart Mountain, far bigger than these. If you look at the topography of the seafloor around Hawaii, for example, there's dozens of mega slides that go out for, I don't know, 200 kilometers maybe, I don't know, but for long, long distances. And so the ocean basins are full of big slides. Yeah. John?
Could you go back to your cross sections?
Yeah.
Let me turn the lights down for a minute on the side.
Oh, it's going to take a minute.
There, right
Yeah.
there. This is fine.
Uh-huh.
The black in this case is a laccolith.
Yeah, this is sort of David's idea of what's going on. You know, we're built over the leading edge of this severe fold and thrust belt. And in southwestern Utah, it's very common for laccoliths to come up into the shallow crust along these zones of weakness, along the thrust faults. And they don't erupt straight away. It's the weirdest thing. They come up within, you know, several hundred feet of the Earth's surface, and they spread out as a sill. And then they inflate. And then the overlying rocks sometimes fail, and that's when you get an eruption. So that's kind of his idea, thinking that, well, during the later stages of the evolution of this volcanic field, as it's inflating, some of those inflation may be due to kind of Laccolithic bodies that are relatively shallow, and providing some initial tilt to the breakaway area and maybe some reason to cause this in the first place.
Injection of gases.
Yeah. Or dikes that could do it and, create stresses within the volcanic field.
So presumably, if I understood in your story about east to west, this laccolith, this intrusive body then is probably inflating from east to west.
You would think, actually, there's probably good reason to think that. And so why did the slides fail to the south versus to the east or something? I don't know. There actually, maybe there were, you hate to argue from lack of evidence, but, this volcanic field, the whole eastern side is part of the Colorado Plateau now that has been, we've lost kilometers of section there of erosion. So maybe there were other slides that are completely gone that we don't know about. But these three very clearly came from north to south, and you can see that based on the skid marks and other kinematic indicators. Yeah.
Now, is there any chance that the Laccolith was actually putting a liquid or gas into the slide plane to get the heat to make the glass?
Yeah, question is the Laccolith directly responsible for no. Directly responsible for, putting some gases or heat or something in to form the glass, the pseudotachyllite, I think no. That's strictly, we see that as a friction-generated melt on these fault surfaces. And as far as, this is wholly hypothetical what these intrusions might be doing, but it's based on what we know to be happening on small intrusions elsewhere in southwestern Utah.
The Laccolith's not exposed anywhere in any of the basement ranges?
No, there's a bunch of Laccoliths exposed. Actually, in these slides as well, something I didn't talk about, there are Laccolithic bodies that came in, shed slides, and then that whole structure is then part of this bigger Markagunt gravity slide. So we've got Laccolith bodies that have been translated kilometers, which is kind of crazy to think about, but yeah.
The lady asked if any of these could be underwater. Could these have even been underwater?
Yeah, question is, could these have been underwater? And no, because at the time these happened, this was a high elevation plateau. We don't know exactly how high, but I would guess, 10 to 15,000 feet maybe is kind of a high plateau, kind of like what we think maybe similar to the Peruvian Altiplano. High elevation plateau studded with volcanic mountains, but it wouldn't have been underwater for sure. Yeah, and in fact, in all these volcanic rocks, unlike here, we never find petrified wood. So we think it was probably dry too, which is a real bummer because I love petrified wood, but we never find it. So, yeah.
I remember hearing that they determined some big landslides on Mars that might resemble this.
Yeah, so question, elsewhere in the solar system, are there structures like this? And yeah, Mars has enormous landslides. On Olympus Mons, the biggest volcano in the solar system, you look at the imagery of that, and it's spread, it's got, these are beautiful analogs to that, yeah.
One of the things that's really interesting, I would submit that part of the reason that this was not really understood or observed is back when you and I and John were trained in geology, the rule was everything happens slowly, millions of years.
Yeah.
But when you look at this and you look at this layer, things had to be going fast enough to melt the rocks. That says a lot.
I think that's one of the key things here that is different from Heart Mountain. Heart Mountain does not have pseudotachyllite per se. It has some really nice ground up fault rocks, but they're not melted. And so Heart Mountain is actually I think most people think it is a landslide generated thing and not a deeply rooted tectonic low angle detachment fault, but there are structural geologists out there that just will not give up on that idea. And it's a bias of kind of where you come from. Are you a structure person? Are you a superficial person? And how you actually describe these things. And so
what you're looking at here had to happen in minutes.
I think you're right. I think this was a really bad day in the early Miocene. It was like, I don't know, 15 minutes, 30 minutes, boom, there was this big cloud of dust and that was it.
That's a violation of some geological rules.
It's totally, and I think why people didn't think of this before, it takes decades, dozens of people decades to map this much territory, something the size of Yellowstone. No one person can do that. And so it took all of this work on mapping, and I'll tell you more about this tomorrow if you're able to come, but a lot of that work had been done before I came onto the scene. So we had people working on extensional things, we had people working on translational things, we had people working on older and younger thrust fault relationships, and they just hadn't gotten far enough along to kind of put it together in any coherent sense. Yeah. Yeah.
Well, you mentioned the dust cloud, but that wouldn't have been something that you can still find?
I'm really intrigued about that. What are the far field effects of this? If something this big, we know Heart Mountain happened, it reorganized drainages and everything. And here, so much of this has been eroded out south of these slides that we just don't have that record. But I'm really intrigued with that question too. I mean, it had to have affected the landscape. And maybe someday someone will look around and be able to tie something unusual way far away to this event. I think that's possible. Yeah. And again, there's some samples of the glass over there. If you don't, I've shown this pseudotachyllite to just countless structural geologists that work in pseudotachyllite, and their jaw just drops open. They've never seen anything like this. It's amazing.
What's the difference with what they
This, normal pseudotachylites, they're these thin, wispy, black things. They're, they can be glassy, maybe not so glassy. This just looks like obsidian. It's glass. It's just beautiful glass. Anyhow, thank you very much. I appreciate the chance.